and this is my demonstration for the Big Data Programming project. The title of my project is a predictive analytic system for detecting boss bunching event using PySpark. In this demonstration, I will explain my project including implementations, code, machine learning models, and finally the working on dashboard. First, let's understand about the problem. Boss bunching happens when two or more buses on the same route end up traveling together instead of keeping an even spacing. It usually starts with a small delay. A late bus collects more passengers at each stop, making it even slow. Meanwhile, the bus behind has a fewer passengers to collect, so it catches up. Eventually, the buses travel together. This creates overcrowded bus, wasted capacity, and unreliable waiting time for passengers. The stakeholder for this project is a transport authority that monitor bus operator performance. This system helps identify where bunching is happening, so they know which route needs attention. Looking at the implementation, I would like to briefly show the repository. This repository contains all the source code, notebook, dataset, and the dashboard. Let's move on to the dataset. For this project, I use two real datasets from the UK Bus Open Data Service for the stage coach operator. The first is the timetable dataset with the routes, and the second is the live vehicle location dataset, which I call it continuously pulling the BODS real API key. Now I will move to the implementation and start with the notebook one. Let's take time. This is the notebook one where I load and validate the both datasets. First I load my pairs timetable CSV. Here the notebook confirmed that there are 476,087 rows with no missing step differences. Next I load the live vehicle locations data. Since boss often report the same GPS location multiple times, I remove duplicate record using the vehicle references and timestamps. This reduced 27,493 raw pulling records down to the 762 unique observations. Finally, I compare both datasets and confirm that 72 routes appear in the both, making them suitable for the analysis. Now that the data has been loaded and validated, let's continue with the notebook 2 where I process the data using PySpark. This notebook brings the data into the PySpark. I create a Spark session using localhost with the 8 shuffles partitions. Then I clean the data by converting coordinate into the double precisions, removing duplicate, repartitioning the data by route, and casting it because later notebooks reuse it several times. Before moving to the next notebook, I would like to show the Spark UI. Here is the Spark UI, which provides the evidence that Spark actually executed these distributed operations. If I open one of the completed states, you can see the multiple completed tasks. These tasks match by 8 partitions configurations, proving that Spark executed the processing across partitions rather than simply running ordinary Python code. Let's continue with the notebook 3. This notebook performs the features engineering. First, I calculate the observed headway between the consecutive bus using the PySpark window-like functions. Then I compare it with the schedule headway using the broadcast join because the timetable lookup table is small enough to fit into the memory. During development, I discovered an important issue. My first model accidentally had a ratio as the input feature. Since the level itself is defined using the value, the model could simply read the answer. This produced a misleading perfect F1 score. I corrected this by removing the features. Instead, I used only genuine predictive features, hour of a day, and the previous headway. Finally, I saved the process data into the SQLite database. I use parameterized SQLite queries with a question mark placeholder, which prevent SQL injections. Let's move on to the notebook 4. This notebook compares the 3 machine learning models. They are logistic regressions, random forest, and the gradient boosting. Here are the regions. Logistic regression achieved the best performance with the F1 score of 0.82 and the ROC curve of 0.90. I also generated the confusions matrix, ROC curve, and the features importance plot. This shows that the previously headway is the strongest predictor. Now let's see notebook 5. This notebook focuses on the exploratory data analysis using PySpark. I calculate the statistical measures including mean, median, standard deviation, skewness, and the kurtosis. Then I detect the outlier using the interquartile range and the method. I also profile the dataset by checking null value and a unique count. A very small headway value often indicates the boss budging, so I demonstrate the broadcast zone. And for the end, I convert the data into the pandas for visualizations using Matplotlib library and C1. Here you can see the visualizations. Now explore distributed computing system. Notebook 6. First, I show lazy evaluations. Spark does not execute transformations immediately. Instead, it waits until an action such as count is called. At the point, Spark build the executions plan and process the data. I also inspect the physical query plan and retrieve Spark reserve and stress metrics programmatically. Finally, let's move to the notebook 7. This notebook repeats the machine learning process using the PySpark machine learning library. I use vector assembler, pipeline, cross-validator, and a parameter grid. The results are consistent with my early scikit-learn models, giving confidence that a model predictive performance is genuine. I also perform a k-means clustering analysis. The best model use k is equals to 2 and achieve a absolute score of 0.796. This group rate according to their tendency to experience the boss bunching. After load, you can see the KPI card showing total row, total bunching event, and the overall bunching rate. I can also filter by the individual and compare the scikit-learn and the ML library model result. To conclude, one limitation of this project is the sample size. The Boss Open Data Service only provides a live vehicle data rather than the historical download, so the number of observations depended on how long I could continuously collect data before the submissions. Instead of creating synthetic data, I choose to keep the dataset completely real and clearly discussing limitations in my critical reflections. Overall, the project allowed me to apply PySpark for the distributed data processing, machine learning with the proper leakage-free evaluations, secure database practice, and interactive dashboard. Together, this satisfy the learning outcomes B1 through B8. Thank you.